Today we are going to take a little digression and speak about a topic that you might think properly belongs in mathematics, but it actually belongs in physics in a very real sense, and this has to do with the way functions look when you sketch them, when you plot them. We are not going to plot graphs to some fixed scale or anything like that, but you see in the study of physics you often come across mathematical formulas, you come across them all the time, and then you would like to know how one quantity varies as another quantity is varied. You would like to know the dependence of x on y or one variable on another and so on, and this happens all the time. We have a mathematical formula, but then it does not speak to us unless we are able to visualize it in terms of a picture which tells you what the function roughly looks like, and I would like to call this the idea of sketching elementary functions. So we are not going to try to plot this on some specific scale. Of course you can program a computer to plot these functions very trivially, but the point about physics is that when you have a formula in front of you, it should be able to speak to you. It should give you information about how these variables change as other variables are changed, and this is very important. A little art, there is a little art to this, and it is the art of sketching functions qualitatively rather than quantitatively. For instance, to take an extremely elementary example, if I plotted this function y equal to x cubed, for instance, that is already a nonlinear function, it is a cubic function. If I were to start sketching this function by linear scales, if I did x here and y here, and that is the origin, and this is 1, 2, 3 and so on, 1, 2, 3 etc. As long as you are between 0 and 1 there is no problem, because this point is a point on the graph. When both are 0 there is a point on the graph here, but the moment you come to 2 here, y has gone to 8, and therefore this graph increases extremely rapidly. It does something like this. So a linear scale is immediately useless as far as such a function is concerned, and since most functions are nonlinear, it is immediately obvious that you should be able to sketch these functions qualitatively without specifying the scale, which can always be put in subsequently. Even when you program a machine or a computer to sketch these functions, you have to display a little bit of cleverness in choosing different scales for the x and y axes, otherwise you do not get any graph that you can recognize. So today I am going to spend a little bit of time telling you how these functions are sketched, what you should look for in these functions, how does the graph speak to you, so to speak, and that will make the subsequent study of physics and physics formulas much more easy for you to understand. When I use terms like this is exponential in something and it dominates over a power law behavior, or such and such a quantity goes to 0 faster than any reciprocal power, inverse power of this variable and so on, it should be able to, you should be able to make sense out of it right away. And for that purpose let me spend a little bit of time telling you how graphs are sketched qualitatively. What do you look for in a function? Let us start with some simple examples. So I am going to start with this example. Of y equal to x to the power n, and we will start with an example of n integer first, positive integer to start with. So here we go, and the idea is to plot everything on the same graph y here, and it is obvious that whenever n is any positive integer, x to the power n and y are exact, and when x is 1, y is also equal to 1, whatever be the value of n. So there is a point here which remains on the graph, and there is a point here which is on the graph, but if n is equal to 1 it is just a linear curve, it is just a straight line, goes off like that. So that is n equal to 1. When n is 2 you have a parabola which passes through the point 1, 1, and the slope here is flat, so it goes like that, it is a parabola. When n is 3 it is an even flatter curve and rises even more rapidly, and when n is 4 and so on it goes even faster. And when n is an even number, the graph is simply reflected on this side, so the parabola is reflected here, and when n is an odd number then the graph bends down and does this, etc. And you can therefore plot n equal to 4, 5 etc. They are going to rise even more steeply after 1, go towards infinity as x tends to infinity, and minus infinity or plus infinity depending on whether n is negative odd or even here. So we have got a graph, we have understood the qualitative behavior of the function x to the power n. But it is interesting to ask what happens if n becomes a fraction between 0 and 1. So again on the same graph, here is y, here is x. I am not even going to mark the unit point anymore. This is what a positive power is going to look like. Depending on how large that power is, it gets flatter and flatter at the origin. X to the 4 is extremely flat, x to the 6 is even flatter, and so on. And here is x equal to n equal to 1, y equal to x. What happens if n is a fraction, like a half for instance? Then too the graph is going to go through 1, but it is going to go like this, say n equal to half. It is very steep at this point. In fact, the slope here is infinite at that point. And this, let us say, is n equal to 2. Okay. It is also going to go to infinity as x goes to plus infinity, but it is going to go slower than linearly, which in turn is going to go slower than quadratically. So now we immediately have this concept of how the function becomes infinite, how fast does it tend to become unbounded. If n equal to a positive integer greater than 1, it certainly increases faster than linearly, and less than 1 it increases slower than linearly. What happens if n is 1/3? Just like x cubed was flatter and steeper, this fellow is steeper here and also goes to infinity, but a little slower. So we have this whole family of curves x to the n, where n is a positive number. As n goes from 0, where the graph goes like essentially goes flat at 1 and remains after that 1 as n goes to 0. As n increases, it goes through the linear graph, and then it goes through graphs which get flatter and flatter at the origin and become steeper and steeper as x increases on the positive side and tend to infinity. Now the graphs for integer values of n, when n is even or odd, are either reflections in this plane or in this quadrant or in this quadrant, depending on whether n is even or odd. So we have the possibility now of understanding that the function x to the power n for general n is one member of a family of curves for all sorts of values of n, and that is the way to understand this simple function here. Okay. Now what happens to a function like log x, for instance? But before that, let us look at a function like the exponential of x. You are familiar with this graph y equal to e to the power x. I presume that you are familiar already with the idea of an exponential, but if not, let me explain very quickly what it is. This number e, the base of natural logarithms, can be defined as the limit as n tends to infinity of a certain number which tends to 1 as n tends to infinity, but raised to a power which increases as n tends to infinity. So it is the limit of 1 plus 1 over n to the power n. That is the definition of this number e. Now it is a remarkable fact that this limit actually exists and is quite finite. In fact, its numerical value is 2.7182818, etc. It is a non-repeating decimal all the way to infinity, an infinite number of places. It is an irrational number. It is called a transcendental number. It is even more than irrational. It is a very special kind of irrational number. But what is remarkable is that you see, when n is a large positive value, 1 over n is a small positive value. So you have a number 1 plus a small positive value. So this number is bigger than 1, and therefore when you raise it to a power, it increases all the time. And now it is raised to a power n, which is itself increasing. So you would therefore think, if you had just 1 here, no matter what you raise it to, you get 1. On the other hand, you have 1 plus 1 over n here, a little increment over 1, and that is raised to the power n. So you would wonder what is going to happen. Is it going to become unbounded because you have a number bigger than 1 and that is raised to a positive value power and is therefore increasing all the time. But the fact is, whatever you are raising, the argument is decreasing here because this is tending towards 1. Had it been 1, like I said, no matter what you raise it to, you continue to get 1. So there is a competition between the fact that this number is tending towards 1 and the fact that this power is tending towards infinity. And the result of this competition is that there is actually a finite limit, and it happens to be this number here. It is the base of natural logarithms, and it is a very fundamental number e. Now extrapolating that a little bit, the number e to the x can be written as the limit as n tends to infinity of 1 plus x over n to the power n for any value of the variable x. You can in fact define it not only for positive values of x but also negative values of x, fractional, rational, it does not matter. You can in fact define it even for complex values of this number x, but we will not get into that now. Is there any other formula for e other than this? And the answer is yes. This is also equal to 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus etc. ad infinitum. This is an infinite series and it converges. In other words, the sum of this infinite number of terms is finite and is guaranteed to be equal to this number here. You can see that these numbers are becoming smaller and smaller as n increases, as you go further and further, and finally in the limit you end up with a number which is convergent, a series which is convergent, converges to this value. Similarly, this quantity also has an expansion which goes like 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus etc. And this too goes on to infinity. And the fact is that this makes sense, this infinite series converges, it is summed and reproduces to a finite sum as you go all the way up to infinity, infinite number of terms, and the answer is e to the power x here. So one could ask, what does this function look like? So let us see how the function e to the power x is plotted, and it goes like this. So here is x, here is e to the power x out here. When x is equal to 0, e to the 0 is 1. So it starts at the value 1, and as x tends towards larger and larger values, it goes up in this fashion and tends to infinity more rapidly than any power of x, any positive power of x. So we say that e to the x tends to infinity exponentially rapidly. That means it goes to 0, it goes to infinity as x tends to infinity more rapidly than any x to the n for any positive n here. But as far as the graph is concerned, I just show it in this fashion. This is not quantitative, as you can see, not on the same scale or anything like that. So this is what e to the x does as long as x is positive. What happens when x is negative? Well, that is easily found because e to the power minus a number, e to the minus x, is equal to 1 over e to the power x. So e to the minus x for negative x, e to the x for negative x remains positive, but it tends to 0 because it is the reciprocal of a large positive number. So it goes to 0 in this fashion here. Once again, it goes to 0 faster than any reciprocal power of x. 1 over x to the 100 certainly goes to 0 when x tends to infinity, much faster than 1 over x to the power 10. On the other hand, e to the minus x goes to 0 even faster, goes to 0 much faster than any power, in reciprocal power, negative power of x out here. So this is what the function e to the power x looks like, but you are guaranteed that the numerical value of e to the x for any value of x, any real value of x, is given by this summing the series or proceeding to this limit, which is a cumbersome way of doing it, but that series there converges very rapidly, and within a short number of terms, depending on what the value of x is, you get the numerical value of e to the x to whatever degree of accuracy that you desire. Okay. So much for e to the power x. Now we could ask, what about the function e to the minus x? What does that look like? It is the reciprocal of e to the x, so we need the reciprocal of this function. So this is y equal to e to the x. I would like to now plot y equal to e to the minus x and that is just the reciprocal of this function. So it goes through 1 once again, but it is the other curve, namely it goes down like this and decreases. So this is y equal to e to the minus x, also remains positive, does this. Okay. Now we ask a little more complicated question. What does the function y equal to x e to the x look like? What does this look like? Okay. Once again, the argument is as follows, and let us plot it for positive values of x so that you can see what is actually happening. For positive values of x, for very small x, remember that e to the power x goes like 1 plus x over 1 factorial plus order x squared and so on. So for x very small compared to unity but positive, this number here is negligible and you have 1 plus x plus etc., and the leading term is 1, but there is already an x here, and therefore this function looks like x near x equal to 0. Looks like x means it does this with a 45-degree slope, and then the higher order terms kick in. Had it been just x, it would go on forever, but because the higher order terms kick in, this function soon starts attaining the aspect of an exponential. Of course it is going to go to infinity as x becomes large positive faster than e to the x, because there is another x multiplying it, but the important thing is to look at the structure of the graph here, and it does this in this fashion. Okay. I leave it to you as an exercise to find out what this function does for negative values of x. It has got to have some continuity here, and it does something on this side, and I ask you to find out what does it do when x is negative on this side. Let us look at what x squared e to the x looks like. So let us plot x squared e to the x. As before, by the same argument as before, e to the x is quite harmless near x equal to 0, it is just 1 plus order x etc., and therefore the leading term is going to come from x squared, which as we know is like a parabola, and then it takes off exponentially in this fashion. So this is the way this graph looks like once you multiply with an x squared, okay, and therefore x cubed, x4 etc. etc. More interesting is the question of what does this look like, y equal to x e to the minus x. What does this graph look like? So here is x and there is y. What would this look like? Again, when x goes to 0, this function here goes to 0, that goes to 1, so the limit is 0, it passes through the origin right here. On the other hand, for very, very small values of x, this function is approximately x, and then there are corrections of order x squared, and approximately x means it takes off linearly, and then it would have continued forever had this been just x, but it is now being multiplied by e to the minus x, which if you recall starts at 1 and goes to 0 in this fashion. So we have the product of a function which starts at 1 and goes to 0 very rapidly, and we have that multiplied by a function which starts at 0 and climbs to infinity not so rapidly because it is a linear function, whereas the exponential drops to 0 much faster. So as x goes to 0, this 0 is going to dominate because it is multiplied by a finite number, so the graph indeed takes off like that, but then once x becomes significant, the function drops back to 0 because e to the minus x is dropping to 0 very fast. So it starts at 0, it is guaranteed to go up, and then it must drop to 0 eventually. So the only thing it can do is to actually go like this and drop down to 0 in this fashion. It is not hard with a little bit of calculus to find out when the peak occurs, but the qualitative structure of this function is clear just by looking at it, by this little way of sketching these functions, that this function here, the product of an increasing function and the decreasing function, where this one dominates for large x, is going to look like this with a single peak. What about x squared e to the minus x? It is going to behave in more or less the same way. The only difference now is going to be exactly the same argument as before, but the only difference now is that near the origin the behavior is like x squared, which is flat at the origin, and therefore you have a graph which looks like this fashion, etc. So one can now multiply it by other functions of x and so on. So the interesting thing is, and this is what is going to happen in general, very often when you have a function, what's of interest are the following facts. Where does it have a peak? Where does it have a minimum? Where does it have a maximum? What does it do for very small values of the argument near 0? What does it do for very large values of the argument near infinity? Does it become infinite for any or become unbounded for any finite value of x, and so on and so forth. How about the function 1 over x? This function is an odd function of x. In other words, when x is negative, it is just the negative of whatever the function was for a corresponding positive value of x. So, in this case, for positive values of x, if this is 0, the function goes down, it tends to infinity as x tends to 0 plus infinity, and as x tends to plus infinity, the function tends to 0. But for negative values of x, it is just the reflection of this graph into the third quadrant, and it looks like this. And as you know, this can also be written as xy equal to 1, which is called a rectangular hyperbola. That is a very special kind of graph, but this is what the function looks like. This quadrant it decreases this way, in this quadrant it goes up in this fashion, just reflected. And of course, in this case it passes through the point 1 1 or the point minus 1 on this side here. What happens if xy equal to 10, for instance? It is again qualitatively just a hyperbola, except it will pass through the point here square root of 10 and minus those values here on this side. Qualitatively it will look exactly like this in this fashion here. So that takes care of 1 over x. How about 1 over x squared? And that is not a hyperbola. What would this function look like? Well, the first thing you got to ask in all these cases is the function an even function of x or an odd function of x? Because if the function is even, you save yourself the trouble, because it is simply reflected on the vertical axis. Whatever happens in the first quadrant happens on the second, and if it is an odd function, whatever happens here happens in the third quadrant here. So this symmetry property is worth always paying attention to, because it will save you a lot of labor. This function is an even function of x. As x tends to 0, it becomes infinite, and as x tends to infinity, it goes to 0. Both these are faster than the way x 1 over x goes to infinity or 0, more rapidly because the power is higher. And on this side, once again it looks on this side, however, it looks like this, and the reason is that this is an even function of x. Okay. 1 over x cubed, it would again qualitatively look like that, except this portion would be sitting out here on this side. So we have y equal to x to the power n for negative values of n as well. We can plot what this function looks like. Okay. How about a function like the following? How about a function like y equal to e to the power x squared? What does that look like? Well, it is an even function of x. So once again, same argument as before, whatever happens here is going to happen here. E to the x squared starts at 0, at x equal to 0, it starts at the value 1, e to the 0 is 1, and increases faster than exponentially, because x squared goes to infinity faster than x itself does. So e to the x squared goes to infinity even faster. It goes off in this fashion, but because it is an even function, this function is steep in this direction. It is not a parabola, it is just a function which looks like a ball and is symmetric about x going to minus x, and it goes off to infinity on both sides in this fashion here. What about the reciprocal of this function? Y equal to e to the minus x squared. That is a very, very important function. It is called the Gaussian. It appears all over the place in many, many physical applications and statistics. So it is worth remembering what it looks like. Here is the x axis, here is 0, and what is the reciprocal of this function? What does it look like? Well, remember that this function is always bigger than 1. Therefore, the reciprocal is always less than 1. And the function is positive, and therefore the reciprocal is also always positive. and as x tends to infinity now e to the minus x squared goes to 0 extremely fast on both sides, and it is a bell shaped curve which therefore looks like this. Okay. So that is what this Gaussian function e to the minus x squared looks like. You will learn a lot more about it in your study of physics as you go along. How about y equal to e to the power 1 over x? What would that look like? Okay. Again qualitatively, because it is fairly complicated function in that sense, but we can sketch what it looks like quite easily. Again, so y is e to the 1 over x as a function of x. Is it an even function or odd function of x? Can we state what it is? Well, since if you put x to minus x and you write e to the minus 1 over x, that is not the same as minus e to the 1 over x. So this is not an even function or an odd function of x, it is mixed. We can't say what it does on this side without examining this function more carefully. But let us argue in the following way. As x tends to plus infinity, 1 over x tends to 0 and e to the 0 tends to unity. So it is clear that if this is 1, this function must go to 0, must tend to this value for very large x. On the other hand, it is a positive number. E to a positive number is bigger than 1 always. So the function remains on top of this graph, and then what does it do? As x tends to 0, 1 over x tends to infinity plus infinity, so e to the infinity becomes infinite. So the function very rapidly increases and drops down in this fashion. What about negative values? Well, if x is a large negative value, 1 over x is nearly 0 and e to the 0 is again 1. So the function is going to approach the value 1 on this side, but because it is a negative e to a negative number, it is less than 1, so it remains below this curve. But then as x tends to 0 from the negative side, it is going to e to the minus infinity. That is like 1 over e to the infinity, which goes to 0 very rapidly. So the function indeed does this. It goes to 0 extremely rapidly and very flat, and it looks like that. So that is what e to the 1 over x looks like for both positive x and negative x here. And once I write that, you should be able to say very easily what does y equal to e to the minus 1 over x look like in this case, because now all I have done is to change x to minus x. So it is immediately clear that the graph is going to look like this on this side, and on this side it is going to do this in this flat portion. Okay. That is just by examining this and saying instead of x I call it minus x, so it is like flipping this graph over, twisting it 180 degrees about this axis, rotating the graph, and that is it. This is what it looks like. So as we come across more and more complicated functions, you will see that I will use such arguments to plot these functions qualitatively, schematically, to try to understand what these things look like. But the take home lesson here now is that the exponential in general tends to dominate over any powers. But when you take limits, when something becomes very large or very small and so on, the general rule of thumb is that the exponential will dominate the issue, and its behavior will dictate what happens when you have a product of such functions. We will have occasion to do many more of these examples as we go along.